Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello students, let us solve question number 27 of 2014 physics paper 2 code 8 question number 27. So let us start with question number 27. Students, let us start with the number 27, which says that a metal surface is illuminated by light of two different wavelengths. There is a metal surface like so is illuminated by two wavelengths. One is 248 nanometer, the other one is illuminated with 310 nanometer. So this is lambda 2 and suppose that this is your lambda 1. Now the maximum speeds of the photoelectrons corresponding to these wavelengths, because when the light is incident the electrons will start emitting. That is because of the photoelectric effect. The electrons will emit from here also. Here this is electron coming out with velocity say u2, and the electron which is coming out from the wavelength of this is, suppose this is u1. This is the maximum speed of the electron that is coming out. So corresponding to the speed, the kinetic energy is maximum kinetic energy, that is called Ke1. So corresponding to this, I'll write the kinetic energy is K1, and corresponding to this the kinetic energy I will write as K2. Okay. Now if the ratio of U1 upon U2, this speed of the electron ejected from this wavelength and this is the speed of the electron from this wavelength, the ratio of the two wavelength velocities U1 and U2 is given as 2:1. The Hc value is given that the Hc value it is 1240 nanometer. So it is the Hc value is 1240 electron volt nanometer. This is electron volt nanometer. This is given. So you have to use in place of Sc this value. The work function of the metal is nearly, so let us say phi is the work function of the metal. Now from Einstein's equation, Einstein's photoelectric equation, the equation is that the energy that is incident, the energy incident is equal to the work function of the metal and the maximum kinetic energy. So from here we are interested in this phi, and that Ke max is E minus phi is the energy of incident radiation which will be obtained from this wavelength. Now Ke max, I have written this, I have to use this equation twice, one for this wavelength and another for this wavelength. So this equation has to be used twice. Now kinetic energy maximum for one is E1 minus phi. The equation is going to change in terms of kinetic energy and the energy that is incident, but this one will remain constant because this is the property of the metal work function. So this is the first equation that I am going to use when I am using wavelength lambda 1. When I will use wavelength lambda 2, I will have kinetic energy maximum equals to E2 minus phi. This is equation number 2. Now if I want to write kinetic energy 1 by 2, then it is half of mass of the electron U1 square divided by half mass of electron, and in the second case it is U2 square. This is E1 minus phi divided by E2 minus phi. I have to divide these two equations. If I divide that, then you can see that this will cancel out. E1 square upon U2 square, but already we have known this E1 upon U2 is 2:1. So squaring both sides, it will be 4. E1 by U2 whole square is 4. So E1 upon U2 whole square, here it will be E1 upon U2 the whole square, which is E1 minus phi divided by E2 minus phi. Now as I told you that E1 upon U2 whole square is 4, so I'll write here 4 is to 1 equals to E1 minus phi divided by E2 minus phi. So our aim is now to find in this equation 4 equals to E1 minus phi divided by E2 minus phi. This is equation number suppose 3. So in this equation, if you put the value of E1 and E2, you will get the value of phi. How to find E1? This answer should be in electron volt, because basically in this case this was not in electron volt, but it was in joule. But because of the ratio, if I convert that joule into electron volt, then also because of the ratio that will cancel out. So this is a number, so nothing to do with that. This phi will be in electron volt. This will be in electron volt if I keep these two in electron volt. That means we know that for any energy of the incident radiation, for any energy that is incident on the metal surface, if I know the wavelength lambda 1, I can get the energy corresponding to that wavelength by using this formula, E equals to 12400 divided by lambda in Armstrong. This would be in Armstrong, and this will be automatically in electron volt. In the question is given electron volt, nanometer, and this and that, so that also you can use, or otherwise you can use that. I will tell you both. If you use this electron volt, the lambda 1 first case was as you can see, the first one, the lambda 1 was 248 nanometer, so that is 2480 Armstrong. Okay, because 1 Armstrong is 10 raised to minus 10 meter, so 248 nanometer, that means 2480 into 10 raised to minus 10 meter, which is obviously 2480 Armstrong. So if I put that here, I will get 12400 divided by 2480 Armstrong. 00 cancels. This is 1240, 1240, and this is 248. So in terms of nanometer, if you want to write, then this will be 248 and this is 1240 electron volt nanometer. You can see here, but anyway, we can get this one. This is in electron volt. So now that I'll use this formula, so E1 is 1240 divided by this is 248. This will be in electron volt. So if I solve this, this will be, because 5 times 200 is 1000 and 5 times 48 is 240. Okay, so this is if you cut this will be 5. So this answer is 5. So E1 is 5 electron volt. So I can substitute E1 as 5 electron volt here. Similarly, we have to find E2 when the other wavelength incident at the other wavelength is 310 nanometer. So if I use that again, then it is 12400 divided by 3100. This is in electron volt, 00 cancels. Then this also 0 cancels. This is 124 divided by 31. If I know that if this is 30, then 34 is 120. So it is 1 here. So 4 times this value will be 124. So this will be 4. So this is 4 electron volt. Now this is 5 electron volt and this is 4 electron volt. We will substitute this value over here and see what we are getting. So substituting this value of E1 and E2 in equation number 3, what you will get. So 4 equals to E1. E1 value we got as 5. 5 minus 5 divided by 4 minus 5. This is equation number 3. After you substitute the value of E1 as 5 electron volt and E2 as 4 electron volt that we have got. Putting that, you will get this. Now you have to solve for phi, that is the work function of the metal. So cross multiplying this goes to that side and becomes 16 minus 4 phi equals to 5 minus phi. This goes to this side and this comes to the other side. This becomes 16 minus 5 is 4 phi minus phi. This 16 minus 15 is 11 and this is 3 phi. So phi will be 11 upon 3 electron volt, because this was always in electron volt. So answer also will be in electron volt. So 11 upon 3 is 3 3s are 9, 2 0, 3 20, 3 6 are 18, 3 6 are 18. Again 3.67, something like that you can say. So if I 67, if you round off this, then it will be 3.7 electron volt approximately. If we look at the options, available options, then 3.7 is here. 3.7, we are also getting 3.7 electron volt. So option number 1 is correct. You can see here 3.7 is here. The other option is 3.2 is not possible and these are less than 3. So this is the only option possible. So this is the answer to this question. Thank you.